In this video, I want to look at applications that involve functions of two variables. There are a lot of different physical problems we can work with that are going to involve two or more independent variables. In other words, I may have multiple conditions that are changing and affect my result. Some common examples include electric potential, manufacturing production models where I have two or more constraints on my manufacturing process, problems that involve ideal gas species, creating and analyzing surface topographies, evaluating the return on investments that involve both interest accrual and periodic deposits over time, or cyclonic weather patterns. I want to give you some definitions that have to do with some prefixes we're going to encounter. The prefixes iso and equi both mean the same, and all level curves have the same z-value. So depending on the context of the problem, I might encounter terms that look like isobar, where I'm looking at lines of equal pressure, isotherm, where I'm looking at lines of equal temperature, equipotential, which are lines of equal electric potential, or isometric, where I have lines of some equal measure. Let's look at an example where I'm going to use the ideal gas law. Many of the gases that exist in nature can be modeled using this ideal gas law that states that PV is equal to nRT. P stands for pressure, V is for volume. Little n represents the number of moles of the gas species that are present, R is the gas constant, and T is the temperature. T is measured in Kelvin. P is measured in Pascal. V is measured in units of meters cubed. N, of course, is in moles. And the gas constant itself, which is R, has the value 8.3 cubic meters times pascals divided by moles Kelvin. I'm going to assume, for the sake of the problems I'm going to be working, that N is equal to 1 mole. I want to use the ideal gas law by setting one of my variables to be my dependent variable and figuring out what happens to that dependent variable when my independent variables each change. So the first thing I'm going to do is take T to be my dependent variable, and I'm going to plot several level curves of the temperature surface in the region where 0 is less than or equal to P, which is less than or equal to 100,000 pascals, and where 0 is less than or equal to V, which is less than or equal to 1/2 cubic meter. In order to make T the dependent variable in my ideal gas law, I'm going to rearrange this. I'm going to get T is equal to PV over little n R. This is the expression that says that T is dependent and my P and V will be my independent variables. When I plot this in a level curve, I get a graph with P on the horizontal axis and V on the vertical axis. My level curves represent constant temperature values, or isotherms. And you'll notice that as my pressure increases for a given constant temperature, my volume will decrease. The bottommost curve on my plot represents a temperature of 1000 Kelvin. My second level curve has a constant temperature of 2000 Kelvin. My third level curve is where T is a constant value of 3000 Kelvin. Again, as my pressure increases, my volume decreases. Now in example 2, still using little n is equal to 1 mole of my gas, I want to take P to be my dependent variable and plot several level curves of the pressure surface in the region from 0 is less than or equal to T, which is less than or equal to 900 Kelvin, and from 0 is less than or equal to V, which is less than or equal to 1/2 meters cubed. Again, I go back to my original gas law, and I'm solving this now for P, so that I get P is equal to nRT over V. I can see that pressure is directly proportional to t and inversely proportional to v. When I graph my level curves with t on my horizontal axis and v on my vertical axis, my isobars show that as temperature increases, my volume also increases, and it increases in a linear fashion. My steepest volume increase occurs when my pressure is at 20,000 pascals. If I hold my pressure steady at 40,000 pascals, you will see that my volume will not increase as rapidly as the temperature is elevated. This pattern continues. If I set my pressure at 60,000 pascals or increase it to 80,000 pascals, my volume will not increase as rapidly as my temperature increases. In my third example, again, with N is equal to 1 mole of gas present, I am going to take V to be my dependent variable and plot several level curves of the volume surface in the region from 0 is less than or equal to T, which is less than or equal to 900 K, and from 0 is less than or equal to P, which is less than or equal to 100,000 pascals. Now I'm going to isolate V in my ideal gas law. I get V is equal to nRT over P, so that volume is directly proportional to temperature and inversely proportional to pressure. When I plot this with temperature on the horizontal axis and pressure on the vertical axis, I can see that for a given volume, as my temperature increases, my pressure will also increase. If my volume is kept steady at 0.05 cubic meters, you can see that as my temperature increases, my pressure increases at a very high rate. But if I let my volume go to 0.1 cubic meters and hold it there, then as my temperature increases, my pressure does not increase quite as rapidly. This continues. If I have a volume of 0.15 cubic meters, my pressure is not going to increase nearly as fast as temperature increases. And if I let my volume take on the value of 0.2 cubic meters, again, my pressure will have a slower increase as my temperature increases. I want to make a very quick note about functions of more than two variables. Clearly, when I use two variables, it's fairly easy to plot in three-dimensional space, either using level curves or using a graphing utility that does a good job at plotting surfaces. Functions in three variables is quite a bit more challenging. These require a level surface rather than a level curve, and including this fourth dimension into our graphing is problematic. A lot of times color or a shading or cross-hatching pattern will be used to represent this added dimension. We are not going to be graphing functions of more than two variables, but it's a good idea to understand how information that is presented in 4 dimensions might be presented. Now you get to try it. Pause the video and read the problem statement and complete parts A through C. When you're ready, restart the video to check your understanding. The problem statement uses the Cobb-Douglas production function, which is given by the function Q of Lk is equal to C times L to the A power times K to the B power, where A, B, and C are positive real numbers, Q is the output function, and L is the labor, and K is the capital. When A plus B is equal to 1, the case is called constant returns to scale. This just means that the output and input both increase by the same scale factor. Let's suppose that A is 1/3, B is 2/3, and C is 40. Let's graph the output function using the window parameters from 0 to 20 on X, 0 to 20 on Y, and 0 to 800 on Z. Then, holding L constant at L is equal to 10, write the function that gives the dependence of Q on K, and then finally we want to hold K constant at K is equal to 15 and write the function that gives the dependence of Q on L. The first thing I want to do with this Cobb-Douglas production formula is graph the output function using the window parameters of 0 to 20 in X, 0 to 20 on Y, and 0 to 800 in Z. When I do that, I get a surface that is increasing in Q as both L and K increase. Now I want to hold L constant at L is equal to 10 and write the function that gives the dependence of Q on K. I'm going to plug in 40 for C, 1/3 for A, 2/3 for B, and 10 for L. My function becomes Q is equal to 40 times 10 to the 1/3 power times K to the 2/3 power. Finally, I hold K constant at K is equal to 15, and my function that shows the dependence of Q on L can be written as Q is equal to 40 times L to the 1/3 power times 15 to the 2/3 power. This video covers a few examples of applications that involve functions in two variables. Be sure and let me know if you have any questions.